Okay, so we're doing a recap of the second half of the 3.4 notes. So in example 3, we were interpreting a velocity graph. And here we saw a snail moving in a straight line. And a snail's kind of good to look at because it does move slowly, and you can actually, would have been cool if we were meeting in person. Maybe we probably need some rain and stuff like that. But you know, if you got a snail kind of like measured, I mean, of course, you can't really assume it's going to move in a straight line. But you know, if you were to kind of like just measure, like, okay, you know, it probably for the first 2 minutes it travels. It accelerates up to 4 inches per minute, okay? And then it stays at the same velocity for a few minutes. And then all of a sudden, it slows down. So instead of staying at 4 inches per minute, it's kind of slowing down a little bit, and it's kind of like almost coming to a stop. It comes to a stop specifically, let me expand that, that's hard to read. It comes to a stop specifically at 7 minutes. Then all of a sudden, the snail decides to turn around. So now it's going towards you, right? If you're considering the snail going away from you being the positive direction, then if it's going towards you, that'd be the negative direction. And in fact, it's speeding up in the negative direction, all the way until it gets like -9 inches per minute. Then it decides to kind of slow down. Maybe it you know, doesn't want to run into you. Stops again at 13 minutes, and then turns around again, and then goes away from you. So that's exactly what's happening physically. Now, speed just is absolute value of velocity. So whenever you do an absolute transformation to a graph, you always take the portion that's below the x-axis and flip it over the x-axis, because everything has to be positive, right? Because if velocity is y and you're doing the absolute value of y, guess what? All the y values are positive, right? That's very easy. We know this, right? Now, just these questions here, like all the different paths. For the first path, it started at 0 inches per minute and traveled steadily for 2 minutes and increased the speed up to 4 inches per minute. Then it traveled for 3 minutes in just constant speed or velocity at 4 inches per minute. What this means is that the acceleration was 0 for path 2, or for interval 2, because we're not changing any velocity. Remember, acceleration is a change in velocity. Then at t equals 7, obviously it slowed down until it got to 0 inches per minute, and it's instantaneously at rest for a brief moment at 7 minutes. The snail's not moving. Then it's moving the opposite direction for 6 minutes, from minute 7 to 13 in that interval, that's interval 4, and does hit a maximum speed of 9 inches per minute, or I guess you could say a minimum velocity, if that makes sense, of -9. But speed-wise, it's 9 inches per minute. When we talk about speed, does not have direction. Like, if you get caught speeding, the officer does not care about your velocity and your frame of reference. If you said, oh, but I'm going toward Tig Hart, that's a negative direction, so I'm actually going negative velocity. Doesn't matter. The cop's still gonna give you a ticket because it's still dangerous, right? You hit a car, you're gonna have a major collision. And then, of course, we're gonna momentarily stop at 13 minutes because the snail has now turned around. Now it's going back in the positive direction in interval 5. And it's steadily increasing speed at that interval. So then we talked about how to write the intervals for when acceleration is positive or negative. Remember, acceleration is positive when your derivative is positive, right? Because acceleration is the change in velocity. So acceleration is the derivative of velocity. Remember, acceleration's derivative, well, it's right there, right? And so you want to see your derivative is positive on your velocity graph, definitely at 1, and definitely from, definitely over here, and definitely over here. So you say from 0 to 2, and from 10 to whatever, 10 to 14 is where we go. Now the part that's really confusing is whether to do closed or open intervals. Now on the AP exam, they are going to ask this kind of question. And sometimes I think just to avoid confusion, they just say, you know what, just keep everything open. But technically, your acceleration is positive at 0 because you have a positive slope. But you don't have a derivative at x equals 2 or t equals 2 because there's a corner. It's not differentiable there. That's why you do an open interval there. And then at 10, we have a horizontal tangent. That derivative is 0, so 0 is neither positive nor negative. So we don't also have a positive or negative acceleration there. So you don't include 10, but 14 is positive. So technically you should be doing brackets there. Then of course, when it's negative, obviously that's when you have a negative tangent line from 5 to 7, and also from 7 to 10, but you can't include 7 or 5 or even 10. You have corners at 5 and 7, of course, and at 10, it's just a horizontal tangent. Now, your speed is increasing, so you're going faster when the velocity and acceleration are the same sign. So when your velocity is negative and your derivative is also of the velocity graph is negative, you're going faster in the opposite direction. Or one is obvious, you're definitely accelerating for interval 1. But interval 3, you're slowing down. Your velocity is positive, of course, you're above the x-axis in the velocity graph, but your tangent line is negative. So whenever velocity and acceleration are opposite sign, you think of that working against each other. So now you're being slowed down. So you're slowing down when the velocity and acceleration are opposite signs. So very important distinctions we have to make here. For example 4, question in the chat. So how are you accelerating from 10 to 13 according to the speed graph? Okay, so from 10 to 13, we are, okay, it's a little confusing. From 10 to 13, let me explain what's happening here. We're slowing down. From 10 to 13, we are slowing down. Now, firstly, velocity is negative and acceleration is positive. And acceleration is the derivative of velocity, right? And the slope of the tangent line here is positive. That's why acceleration is positive. So the acceleration is going in whatever you're defining as a positive direction. Let's say the snail is going away from you. That's a positive direction. So it actually is changing its velocity in that direction, if that makes sense. But the velocity is still negative because it's still going towards you. Think of it this way. It's kind of like when you're hitting the brakes on your car, right? You're still moving forward, but you're decelerating. So you're slowing down. Now, in this gets a little weird. You're going the opposite direction and you're accelerating. But the fact that velocity and acceleration purely are opposite in sign, it's actually slowing down. But yes, acceleration is positive because formally acceleration is a derivative of velocity and you have a positive tangent line. So don't overthink it too much. It is coming to a stop, but that's because your velocity was going the opposite direction and your acceleration is going in the positive direction. So that's what's happening there for that one. So acceleration is positive, but you are slowing down from 10 to 13. So what we could do actually, I probably should actually do this really quickly. Your speed is increasing, and you could just look at the speed graph, right? Your speed is increasing from 0 to 2, and also from 7 to 10. So that's where you have positive slopes, and also from 13 to 14. So our speed is increasing. Now in this case, because you want both of these to be positive or negative, it's gonna be a lot easier to use open intervals. This is where the AP exams, like, let's just use open intervals, just avoid the confusion. So your speeds increase from 0 to 2, from 7 to 10, and from 13 to 14. And you use these little union symbols for that. Your speed is decreasing from 5 to 7, and from 10 to 13. That's where the velocity and acceleration have opposite signs. But because you have a speed graph, you could just say, hey, I'm increasing the speed from 0 to 2. I'm increasing the speed from 7 to 10. I'm increasing the speed from 13 to 14. I'm decreasing the speed from 5 to 7 and from 10 to 13. Because you see the graph is dropping, right, for speed in those intervals. And of course, the speed is constant from 2 to 5. So the speed graph could be helpful in that regard as well. So hopefully that could provide some consistency for understanding this stuff. Then for example 4, we had a function to model the projectile motion of some rocket. Actually, it's not technically projectile motion, it's going straight up and down. So it's not technically, it's kind of like those little pop rockets, like you kind of like, press and it goes up and down. It's not going to be going horizontally. That's going to be a little bit different. That's involving two-dimensional motion. And we're not going to really investigate that just yet because we're not ready to do that yet. But this is just going straight up and down. Just kind of like you throw a ball up and it comes back down again. And that's the equation that governs it. So how high does it go? You don't have to use calculus for this. I would actually just factor, find the x-intercepts, and then use symmetry to find the vertex. So the vertex would be at x equals 5. Plug in 5 into the original equation, and you're going to get 400. So you could just use just basic algebra skills for that one. You don't have to use any calculus whatsoever. You can use calculus to determine that. We will, but you could just do that instead. Or if you might remember from your Algebra 2 class, negative b over 2a finds you the x-coordinate of the vertex, where b is 160 and a is negative 16. That works too. So once you find, again, the x-coordinate vertex, plug back into the original equation to get the y-coordinate of the vertex. So it hits a maximum height of 400. And then what is the velocity and speed of the rocket when it's 336? So 336 is over here, or probably over here. So you're trying to find the slope of the tangent line there. That's where we're actually going to take the derivative of position, right? So again, we have a position equation, and we use that to figure out the height. But if we take the derivative of that, which is real easy, negative 32 plus 160, then what you can do is you could just set it equal to 336 and solve for t. And we get two different possibilities. And it's on its way up at 3 seconds, on its way down at 7 seconds, because graphically that's what we see there, right? Again, that's at 3, and that's at 7. Okay, so we have that all hashed out. And by the way, if you do set the velocity equal to 0, because you are momentarily stopped, like it kind of like stops momentarily and then comes back down again. It's kind of like if you throw a baseball up and down, or if like if you have a batter who like pops it up and it just goes straight up and the catcher catches it, right? You could just also realize that the slope of the tangent line here is 0, and you can set that equals 0, and you will get 5 anyway to help you answer part A. And if for part C, when it hit the ground again, just find the other x-intercept. That's 10. You don't have to use calculus for that. That's just pretty straightforward. Don't worry about this stuff here. I decided not to do that. Again, I just don't know if we're quite ready to do that yet, so I didn't feel like doing parametric mode for this. We'll revisit that later. Obviously, this is not filled out, but marginal cost, you guys are going to break out room and do a problem deals with marginal cost. Marginal cost can be really important in the business world because, like, say, for example, you have a factory, and you're wondering, if it's viable to keep your factory open, especially, in the time of a pandemic. What if your production is down? Because you already have fixed costs also, right? Like you have the cost of just having employees around, the cost of the electricity or utility, stuff like that. But of course, when you make more items, you should make more money. So you're kind of curious, like, what is my potential profit if I'm making 5,000 items compared to 10,000 items or 10 items? And so the derivative gives you that instantaneous rate of change, because if C is cost, then the derivative will be the cost per item, because you're taking a derivative with respect to X, and X is representing the number of items you're making. So f prime of X, the units are going to be the cost per item. And then this would just mean that if you make 5,000 items, the cost per item is 14 cents, I guess. And then which one do you think would be a bigger value? My thinking is that the bigger value would be f prime of 10, because I'd assume that if you're only making 10 items and you have all these other fixed costs like your rent and whatnot, that's going to just cost you more per item. Whereas as you're making more items, the cost goes down. So maybe you don't keep the factory open if you're only selling 10 items, but maybe you're up and running when you have orders for more items. And we call it marginal cost. The other part we're going to do in the breakout rooms are these AP style problems that involve tables. They love doing this on the AP exam. So this came from the 2001 exam. And here they're looking at temperature of water at a pond versus days. And so done over a 15-day period, and the intervals are nice to space out every 3 days. And they're asking for W prime at 12. Now, you don't have an equation for W, but don't worry about it. If you have 2 points that are below and above 12, like when T is 9 and T is 15, then what you could do is you could just draw a secant line between 9 and 15, and just assume that the tangent line at 12 would be the same as the secant line between 9 and 15. They're going to be kind of close enough, so if I draw a secant line between A and C here, calling A T equal 9, C T equal 15. Okay, I kind of missed there. I could do better than that. And a tangent line B, they're going to be roughly the same slope. So you would use that as an estimate. That's all you do. So you just do the secant line between 9 and 15, and that would be sufficient. Actually, that's what they want. That's what they want you to do on the AP. And likewise over here, now here they want the derivative of 45. Now in this case, they're looking at gallons per minute versus minutes. So your units are going to be gallons per minute squared. So it's almost like an acceleration volume, if that makes sense. Now in this case, you're not given 45 in the table, but 40 and 50 are above and below, and they're symmetric, right? Because 45 is halfway between 40 and 50. So you can do the secant line for 40 and 50, and you're good. That's all you're doing for those problems. So that pretty much is a recap of the second half of the 3-4 notes. Now I want you guys to practice doing some of these problems. So I did, I'm asking you guys to kind of do a problem like example 5 here, and like example 6 and 7. So if you go to your email, you can see I sent worksheet 13, and I also sent an image. If you have the textbook at home, great. So you guys are going to be doing number 27, page 140, or just use your email. That's fine. Worksheet 13, hopefully you picked it up from Sacred Heart, or you downloaded Schoology. Also, just emailed it to you. So you're going to work through that so you can see. Excuse me. You can see here that these problems are very similar to example 6 and 7. So you'll work through that, and we'll go over your responses. And of course, right here, there's an image. It's about marginal cost, and you're working that out also. So, and you have the answers in blue. I don't have the answer for worksheet 13, so I'll just share that when we come back from the breakout session. So I have 15 minutes dedicated for the breakout session. I think that should be sufficient time. I did take more than I had anticipated to do the recap of the second half of 3-4 lesson. I should always budget more time for that, but that should be fine. So we'll come back at 9:40. Then we come back, we'll talk about, that'll take us about to 9:45. And then that should be enough time to do the rest of, to do the 3.5 notes. And of course, review any 3-4 homework. So anyway, let's go to breakout rooms right now. So we have 18 people here, I believe. So let me stop sharing.